All right, so here for lecture 18, we're going to be finally moving away from glucose entirely, and we really won't come back to glucose metabolism per se again in this course. As I've been alluding to for a while now, when we come back to photosynthesis with our last two lectures, we're going to have an easy time with that topic because it's actually the glucose metabolism story we have been telling all along in reverse. But it will be distinct and different specific to plants. But for this lecture, these three chunks of lecture 18, we will be talking about nitrogen metabolism, really switching gears pretty extensively from where we've been, topics we've been speaking about for the last 8 lectures or so. So the entire lecture series will start off talking about how nitrogen is fixed from the environment, how nitrogen is taken out of the air, out of the nitrogen gas that's in our atmosphere and used for nitrogen-containing compounds. And then we'll spend the bulk of our time on the anabolism of nitrogen-containing compounds, how we make amino acids specifically. We'll touch upon the essential amino acids as part of that discussion, a side note, but still something important to talk about. These are the amino acids we can't make and we have to consume through our diet. And then, as we always do in metabolism, we'll talk about the other fork in the road, the catabolism, or the breakdown of nitrogen-containing compounds, the breakdown of amino acids, and that will lead us to our second cycle of this course, the urea cycle. And we'll end with that in chunk C. So through this course, so far, we've come across many molecules that contain nitrogen, molecules such as amino acids. Heme is a nitrogen-containing compound. Of course, the nitrogenous bases that go into making nucleotides, no surprise they contain nitrogen. And so we've been dancing around nitrogen-containing compounds for quite a while in this course, but we've never really talked about the metabolism of nitrogen itself specifically. What we have been discussing, whether we've realized it or not, is the metabolism of carbon, hydrogen, and oxygen. Remember, carbohydrates are hydrated carbons, and so really we've been focusing on these three atoms, essentially the ingredients of sugars. Nitrogen is important. It's important for biochemistry. It's important for keeping us alive. Nitrogen-containing compounds are some of the most important biomolecules in our bodies, and so we do dedicate this one lecture at least to scratching the surface of nitrogen. And nitrogen is some pretty wicked stuff. Ammonia is one of the simplest nitrogen-containing compounds, and ammonia is lethal, actually. Ammonia could be a deadly gas if breathed in high enough quantities. But this toxicity of nitrogen is really only true of some forms of nitrogen-containing compounds. In other forms, in other respects, nitrogen is essential for life. So today we're going to talk about nitrogen and the double-edged sword that nitrogen really is, how it can be toxic and how the body contends with that toxicity, and how it is needed and how the body contends with that essential need. So essentially we'll start the lecture series by talking about getting nitrogen out of the air, and then how we get that nitrogen into amino acids, and then how we get those amino acids broken down metabolically, and how we get this toxic nitrogen out of our bodies. What we will not discuss in this course or as part of this lecture series is nucleotide metabolism. Nucleotide metabolism is probably one of the more complicated topics of biochemistry, and we will not be discussing that. So the pentose phosphate pathway that is the primary feature of nucleotide metabolism, and this is not something we cover in this class. So let's start where I told you we would start. Let's talk about general nitrogen metabolism, how we get it out of the environment. Nitrogen fixation is the process by which nitrogen gas, molecular nitrogen, N2, from the atmosphere is incorporated into ammonia. Ammonia, again, being the simplest type of biomolecule that contains nitrogen. And then from ammonia, that nitrogen can get into a lot of different other nitrogen-containing biomolecules. Nitrate ion, that's NH3, negatively charged NH3, is another source of environmental nitrogen. Most fertilizers contain this form of nitrogen. These are the nitrate fertilizers that some of you may have heard of. And nitrates are reduced to ammonia by the process of nitrification. So already, perhaps, you appreciate that one way or another, the nitrogen that we obtain from the environment is going into ammonia. Ammonia really is the starting point of biologically relevant nitrogen. Whether that nitrogen is coming from nitrogen gas or that nitrogen is coming from nitrate ion, that nitrogen is eventually going to wind up in ammonia. Once it's in ammonia, this nitrogen can, again, like I just said, be used to make a lot of different organic biomolecules, for our purposes most notably amino acids. Denitrification kind of goes the other way. This is the idea of converting nitrate and nitrite ions, that's NO2 negative, back into nitrogen gas. And so we're starting to get the sense that there's a cycle here, that nitrogen comes out of the environment, starting with nitrogen gas, and nitrogen can go back into the environment, once again becoming nitrogen gas. And of course, that is true. That is the nitrogen cycle. Once made by living cells, either through nitrogen fixation or nitrification, ammonia is converted into the only usable source of nitrogen by plants and other living cells, and it's this form of ammonia, this form of nitrogen, that's passed to animals through the food chain. So here we get to this idea of the nitrogen cycle. Animal waste that is produced after consuming nitrogen-containing compounds, this is the excreted waste, urine, P, is composed mostly of urea, another nitrogen-rich molecule. We'll talk about how we make urea towards the end of this lecture series. And that urea is converted into ammonia by microbes, and that ammonia can re-enter the atmosphere as nitrogen gas. The death and decay of animals and plants results in the production of ammonia gas as well. And denitrifying bacteria, not surprisingly, are responsible for denitrification, and that reverses the conversion of ammonia to nitrate, and then we can make nitrogen gas that goes back into the air. So here it is in all its glory, the nitrogen cycle. We have, let's start with the nitrogen in the air, I suppose. Nitrogen in the air can be converted into nitrogen-containing compounds, nitrate ions, as well as ammonia through a host of different processes, which I'll cover in just a minute. And then that nitrogen becomes fixed into plants as amino acids, as nucleotides, and things like that. Animals eat the plants, animals pee on the ground, and some of that nitrogen can re-enter the nitrogen cycle through urea, through urine. Animal dies and rots on the ground, and that nitrogen can re-enter the environment as ammonia gas and be denitrified back into nitrogen gas through denitrifying bacteria. And of course, we industrially use nitrogen as well by creating nitrate ions that we can use as fertilizers, which enter the plants, which enter the food chain, and then go back into the plants and back into the ground through pee and decay. And so we have this constant cycle of nitrogen. In fact, the nitrogen that's in your body right now, making up all of your amino acids and your nucleotides, was undoubtedly created by the birth of our own sun. One of the major byproducts of new star formation is nitrogen molecules, nitrogen gas, N2, and it's that nitrogen that seeded our original atmosphere, and it's that nitrogen that's in us right now. So the old kind of hippie adage that we're all stardust is very much true. All of the atoms in our bodies right now are literally stardust, the dust cast off by newborn stars that eventually came into the molecules that make us us. So in this lecture, we're going to discuss the overall generalities of amino acid metabolism only. Again, do know that I'm dropping nucleotide metabolism from this course for the sake of simplicity and time. So nitrogen fixation. All of the nitrogen atoms in our body ultimately came from nitrogen gas in our atmosphere. There's no other place for us to get nitrogen other than from nitrogen gas in our atmosphere. And that nitrogen gas, that molecular nitrogen N2, is reduced to ammonia by this process that we are calling nitrogen fixation. Now there's a problem here. Nitrogen gas, N2, molecular nitrogen, is composed of a triple bond between the two nitrogens that make up molecular nitrogen, and those bonds taken together, all three of them, have a combined bond energy of 940 kilojoules per mole. That is a lot. That's the equivalent of about 30 ATPs that are needed to break all that. That's a lot of energy. Nitrogen is a noble gas. Another way of saying that is that nitrogen is very, very happy being nitrogen gas. It is inert, non-reactive, and it does not want to separate. There's no high transfer potential for anything. It is not reactive. Nothing's going to happen. Nitrogen wants to stick to nitrogen. Unless something very actively and energetically goes and makes nitrogen split from itself. And this is where bacteria come in. Bacteria, from a living system's perspective, are solely responsible for reducing nitrogen gas to ammonia. Plants then use this ammonia created by these bacteria directly to make nitrogen-containing molecules. It's almost like a natural fertilizer. In fact, ammonia is such a good fertilizer that ammonia gas would be the most efficient fertilizer we could use to fertilize plants industrially. If we were able to aerate farm soil with ammonia gas, we would have the most potent, efficient fertilizer around. We would actually also have a lot of dead farmers because ammonia gas is so toxic. So we don't use ammonia gas as a fertilizer simply because of its toxicity. Ammonia is so precious to plants and bacteria solely responsible for creating ammonia that many plants that we consider to be some of the most robust, like alfalfa, have formed a symbiotic relationship in order to achieve this type of ammonia. So these nodules here in the roots of these alfalfa plants are actually hollow nodules filled with bacteria. Bacteria who have safe haven in these roots and whose sole job is to create excess ammonia for these plants. So a very symbiotic relationship between the bacteria and the plants. It's almost like a large-scale version of the relationship between our own cells and mitochondria. The plants give the bacteria a safe place to live, and the bacteria make excess ammonia to feed the plants. Many free-living bacteria and blue-green algae are also capable of fixing nitrogen from the air, so this isn't specific to the bacteria that grow in plants. Perhaps surprisingly to some of you, we do not have the ability to fix nitrogen at all. We have no metabolic process for fixing molecular nitrogen from the air, nor do any plants. Plants rely solely on the action of bacteria to make ammonia for them. About 60% of all newly fixed nitrogen from the atmosphere is fixed by microbes. They really are shouldering the heavy burden of this. Lightning and UV radiation from the sun fixes another 15%. Lightning! Again, really emphasizing how much energy it takes to separate the two nitrogen atoms of molecular nitrogen. So we're up to about 85%. And believe it or not, the last 15% we fix with all of our industrial activities making nitrogen-containing fertilizers. When that's done industrially, fixing nitrogen, that is, making nitrates from nitrogen gas, requires a metal catalyst, 500 degrees centigrade, and 300 atmospheres of pressure. That's the energy required to split molecular nitrogen. Those triple bonds have a lot of energy, and we must put in an equal amount of energy to break them. Bacteria do the very same process at room temperature and 1 atmosphere of pressure. Simply amazing. Bacteria are so much more efficient at fixing nitrogen than we are as people. The molecular machine used by bacteria that's responsible for fixing nitrogen in this way is called the nitrogenase complex. Again, we simply mean that this is a protein complex, an enzymatic complex, that has the ability to make ammonia from nitrogen gas. And we won't go into the process in all that much depth at all. One, because it's highly complex, and two, because different plants do this, different bacteria do this in different ways. But the half reaction of reduction for this reaction is always the same, and this is what it is. You have one molecule of nitrogen gas, of molecular nitrogen, 8 high-power electrons, 16 ATPs, and 10 protons will become 2 molecules of ammonia, those 16 burnt ATPs, the 16 inorganic phosphates that were released, and 1 dimolecular diatomic hydrogen gas. That's a lot of energy. 16 ATPs and 8 electrons, all needed to make 2 measly little ammonia atoms, molecules. 6 of these 8 electrons are used to reduce the molecular nitrogen itself to ammonium, and that's what we see here. Here is the triple bond, each a pair of shared electrons. So this is the molecular nitrogen, and here are the 6 electrons and the 8 protons. And we can actually track where those electrons were donated to break these bonds and where the protons came in to make those new bonds with those new nitrogens. The last 2 electrons that we haven't accounted for yet are the 2 electrons that are used to make that molecular hydrogen. So this total reaction is an 8-electron reduction reaction. The half reaction of oxidation I do not provide because different plants do the oxidation side of this reaction differently. In the end, the oxidation is simply a means to harvest the electrons and the protons to do this reduction anyway. So however plants are doing the oxidation half reaction, it's simply a way to generate electrons and protons for the half reaction of reduction that I just showed you. In principle, the way the nitrogenase complex works is that it's just a series of many, many redox reactions. Obviously, that's really the whole purpose here, put together into a chain that ultimately culminates in the reduction of nitrogen to ammonia gas. And perhaps ringing a bell for some of you, this chain of redox reactions includes iron-sulfur clusters and ferredoxin, and so yes, it does have some basic similarities with the electron transport chain. Electrons flow in one direction, they change hands down the line, and again, I'm not going to hold you accountable for this figure at all, but I just want to give you some sense of what's happening where, that electrons are being passed from ferredoxin to an enzyme. In order to pass those electrons once more, we need a lot of energy. That's where the ATP comes in. Another redox enzyme does the actual reduction of nitrogen itself, and out the other side comes the ammonia gas. Approximately half of the ATP that's generated by green photosynthetic plants is used for this reaction and this reaction alone. Let me say that again. Half of all the ATP that photosynthetic plants make, they make solely to fuel the nitrogenase complex in this way, to keep bacteria growing near them, so that those bacteria will make ammonia gas. That's how important it is for plants to get nitrogen. That's how important it is for the food chain to get nitrogen. So to summarize this introduction into nitrogen metabolism in general, we define nitrogen fixation as the process by which nitrogen gas, molecular nitrogen from the air, is made into ammonia gas, and bacteria are responsible for doing this in living systems. It's bacteria that make ammonia for plants. The molecular machine responsible for fixing nitrogen in certain bacteria is called the nitrogenase complex, and we very briefly and kind of superficially went over how that complex works. Now that we've made ammonia, we can use that ammonia as a source of nitrogen for the building of amino acids, and that's where we will go next in Chunk B.